all the modern physics is predicated on the existence of the laws of nature or the laws of physics. And the whole goal of physical science is basically um, to discover them and study them. And today I will discuss can this idea be wrong in some sense? What does it even mean? Uh, I decided to record this video because I just came across an interesting paper which attempted to challenge, this whole notion. Let me show you it. It's a paper by Paul Davies called The Implications of a Cosmological Information Bound for Complexity, Quantum Information, and the Nature of Physical Law. So let me just kind of read you parts of it, especially the introduction, where he lays down his idea. First, let me articulate the orthodox position adopted by most theoretical physicists, which is the laws of physics are immutable, absolute, eternal, perfect mathematical relationships, infinitely precise in form. The laws were imprinted on the universe at the moment of creation, at the Big Bang, and have since remained fixed in both space and time. The properties of the physical universe depend in obvious ways on the laws of physics, but the basic laws themselves depend not on iota on what happens in the physical universe. There is thus a fundamental asymmetry. The states of the world are affected by the laws, but the laws are completely unaffected by the states. And a dualism that goes back to the foundation of physics with Galileo and Newton. The ultimate source of the laws is left vague, but it is tacitly assumed to transcend the universe itself, i.e., to lie beyond the physical world and therefore beyond the scope of scientific inquiry. The proper task of the physicist is often said is to discover the forms of the laws using reason and experiment, adopt them pragmatically, and get on with the job for determining the consequences. Inquiry into the origin is discarded as quasi-religious quest. The orthodox view of the nature of physical laws conforms well to the mathematical doctrine of Platonism. Plato regarded mathematical forms and relationships as enjoying a real existence in the otherworldly realm, where mathematicians come upon them on a voyage of intellectual discovery. A Platonist regards mathematics as possessing an existence independent of the physical universe, rather than being a product of human brain. An essential quality of the Platonic heaven is that the mathematical forms it contains are perfect. For example, circles are exactly round, in contrast to circles in the physical universe, which are always flawed approximation to the idealized Platonic forms. Most theoretical physicists are by temperament Platonists. They envisage the laws of physics too as perfect idealized mathematical relationships and operations that really exist, located in abstract realm transcending the physical universe. I shall call this viewpoint physical Platonism to distinguish it from mathematical Platonism. Newton was a physical Platonist and cast his laws of mechanics and gravitation in terms of what we would now call real numbers and differentiable functions. Taking Newton's laws seriously implies accepting infinite and infinitesimal quantities and arbitrary precision. The idealized Platonic notion of the laws of physics reached its zenith with the famous claim of Laplace concerning an omniscient demon. Laplace pointed out that the states of a closed deterministic system, such as finite collection of particles subject to the laws of Newtonian mechanics, are completely fixed once the initial conditions are specified. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at any given moment knew all the forces that animate nature and the mutual position of beings that compose it. Um, if the syntax were vast enough to submit the data to analysis, could condense into a single formula the movement of the greatest bodies of the universe and that of the lightest atom. For such an intellect, nothing could be uncertain, and the future, just like the past, would be present before his eyes. Yeah, okay, so that's the idea of the Laplace demon, that the universe is fully deterministic because it's governed by the laws of nature, and if we know the past perfectly well, we could predict the future. Okay, he continues. If Laplace argument is taken seriously on the assumption adopted, then everything that happens in the universe, including Laplace's decision to write the above words, um, my decision to write the article, Chatin's beautiful work on Omega, etc., are all preordained. The information about these events is already contained in the state of the universe at any previous time. To get some idea of Demon's gargantuan task, note the following. If the demon overlooked the gravitational force of a single electron located at the edge of the observable universe, then his prediction for the motion of a given molecule of air in your living room would be rendered completely uncertain after only 12 intermolecular collisions. This arresting example reveals how exquisitely sensitive to error predicting the future can be. Laplace vignette is based on classical mechanics and is usually dismissed by invoking quantum mechanics or arguing that the universe is an open system, but this misses the point. So yeah, I don't think quantum mechanics resolve this problem. Um, it just gets more weird, I would say. The real absurdity in Laplace statement is an implicit reliance on the physical Platonism, extrapolated to a staggering degree, made without any experimental foundational whatsoever. In spite of the fact that we now know Newtonian mechanics is only an approximation, physical Platonism remains the dominant philosophy among theoretical physicists. The approach of quantum cosmology, for example, is predicated on the assumption that the laws of quantum mechanics and general relativity exist independently of the universe, and may therefore be invoked to explain how the universe came to exist from nothing. In the fashionable subject of string and M theory, the string Lagrangian or whatever else serve to determine the unifying dynamics is assumed to somehow already exist, so that from it may one day flow an explanation for space, time, matter, and force. So, okay, yeah, that is the orthodox view, as he called it. Now, we could try to read what he offers as an alternative. A completely different view of the relationship between mathematics and physics comes from Chaitin's development of algorithmic information theory, from which he was drawn to the conclusion. A scientific theory is like a computer program that predicts our observations. For example, in Newtonian mechanics, the initial positions and momentum of a system of particles serves as input data. The laws of mechanics are the program, and the final state of the particles at some later time of interest corresponds to the output. In this manner, the universe processes information automatically as it evolves. So we might envisage the laws of physics in terms of software as a grand cosmic computer program. Now, of course, he asks, the shift of perspective, simple thought it may be, has profound applications, which are immediately apparent when we ask what is the hardware on which the cosmic software is being run. The answer is, of course, the universe itself. And by this I mean the real physical universe. Yeah, so it's some sort of simulation hypothesis, I guess, or computational universe theory. We had some theories like this around. Indeed, I think he claims that Chaitin was the first one to propose something like that. I don't know for sure, probably it's true, and yeah, it inspired other people. Uh, it's just a question, what does theories actually do and how do they replace notions of the laws of physics. One of the most famous among them is Stephen Wolfram's um, cellular automata theory. So essentially what happens in it, um, we replace the the four-dimensional smooth space-time with some sort of discrete hypergraph with simple evolution rules, which in the end kind of approximates our four-dimensional universe. Yeah, and because like the steps are very, very small, we don't really see it, right? We don't really see the discreteness. And some mathematicians who joined this Stephen Wolfram project, they were able to prove that under certain assumption on this hypergraph dynamic, the Einstein equations, they emerge as an effective theory. So that's one of the way we could think about the laws of nature as being, emergent and not fundamental, right? At least here the general relativity is an emergent property of this hypergraph dynamic. However, I couldn't just say that, we successfully replaced the notion of the laws of nature with something else, because now what we did is we just took this simple graphs transformation, which describes here in these pictures, as the new laws of physics. It's just basically saying that that's how nature works, right? That this is our, replacement of string theory. And just instead of saying, well, the actual gravity is like made out of strings, we now say that no, gravity is made out of this hypergraph transformations. And these rules which he described are kind of the rules of nature. So there's no really true paradigm shift here. I don't know what is the fundamental discovery. It's more like just a new theory of everything with its own laws. So maybe Paul Davies means something else, or is it just something I can't understand here? What happens is just one law got replaced with another. It's hard to imagine, yeah, what is the opposite of having a law? Isn't it just chaos, total unpredictability? But it seems like it sounds like giving up. We know that the universe could be predictable to some point, and that's what the notion of law mean. Yeah, so the rest of the paper is dedicated to the study of the constraint imposed on the computational power of the universe by the cosmological horizon, uh, um, employing the Bekenstein information bound on the number of information which could be stored within the horizon. So he said that, well, yeah, if we have a cosmological horizon, the Hilbert's space of the universe is actually finite dimensional, so it poses a bound on how much information we could process in it. And he concludes that Laplace demon is literally physically impossible. There is another paper I found on this topic, which you might be interested in. It's called What Computer Science Has to Say About the Simulation Hypothesis. And he kind of dives deeper into this question. He introduces the notion of, the PCT and RPCT universe, The one, I think, the PCT universe is the one which could be modeled on a Turing machine, and RPCT universe is the one which has a Turing machine in it, right? Because that's indeed kind of non-trivial. Like in the Paul Davies paper, he assumed that the universe is finite, or at least the cosmological horizon imposes the constraint on the computational power of the universe, like, which means that it cannot have like a universal Turing machine, because universal Turing machine has to be infinite, right? Because like an infinite space of states. And in this paper, well, certainly he concludes that, yeah, well, he mostly considers like infinite universes, because if the universe is finite, that's all. It doesn't have a Turing machine. And it's kind of funny because in his setup, for some reason, he considers universe which is like finite outside of the Turing machine. I don't know what he does. It's like all universe is mostly a computer, and like the rest is kind of finite. Yeah, well, I would say, but he still raises interesting points. Like, can our universe be even simulated on a Turing machine? Can our universe have the Turing machine inside of it? And what are the requirements for one universe to be able to simulate another one? And could we do it multiple times? Because it seems like we are losing something in each simulation step. For example, if you try to simulate the dynamics of quarks on our laptop, right, we are using the dynamic of electrons to do it, right? That what actually happens. The electrons inside our laptop, in all those electronics, moving in such a way that they encode the laws of evolution of quarks, like when we try to model quark-gluon plasma. But we certainly making this dynamic less effective, less effectively stored. Like we used way more space and you know, computational power, I guess, to like simulate the evolution of quarks and the quarks themselves need. So yeah, it seems like we would run out of space eventually. We could not embed simulation to simulation forever. Yeah, and it seems like it should be even impossible to simulate our own universe by this kind of logic. However, he arrives to different conclusion. Yeah, you could look on this paper for yourself. The last thing I want to mention is that it's not the first time I came across somebody who challenges the notions of the laws of physics. Here is a good video about it by James Elias from Inductica. I'll play a small clip. He gave two examples of, reasoning from movies. So if you don't want spoilers, watch the whole video from start. But I play the small part.
The error common to the two examples I gave, the primitive superstition that is still strongly embedded into our scientific worldview, is the belief in laws of nature. Progress requires that we throw this primitive notion in the garbage in favor of a simple alternative. Regularities don't exist because nature follows laws. What are laws? Instructions issued by God? Instructions issued by the universe at large telling entities what to do?
So, yeah, but let's look what kind of alternative he proposes.
No. Entities simply exist and have natures, and they act on one another in accordance with those natures. The men on the temple steps thought that existence just had a downness to it. Things go down. That's the rules. Similarly, Torricelli's contemporaries held the statement, nature abhors a vacuum, as a kind of rule of nature. When you make a vacuum, nature fills it. Them's the rules. Hypatia overcame this error. by thinking in terms of entities acting. Instead of thinking that there's just a fundamental downness to existence that would cause people on the bottom of a round earth to fall off, she instead asked what entity might be causing the downness. She asks, what mysterious wonder might be lurking beneath the earth that pulls everything in? This is a first step towards a model of our solar system, a theory of gravity, and a means of navigating space. In like form, Torricelli may have made his discoveries by asking what entity causes the water to get pushed up. This reorientation opens the door to atmospheric pressure and fluid mechanics, a field which allows us to predict the weather, augment forces with hydraulics, and many other wonders.
So yeah, so basically, um, he proposes a different kind of concept of entities and their nature and causes between them, right? That one entity causes something on another entity, or I don't know how to say it correctly, but I feel like the problem which we'll run into is, well, the same problem as with computational universe, that there will be laws governing these causes and the behavior of entities. So I don't know what is the new perspective here. Yes, sometimes it's useful to think in terms of entities, right? The example I give in the comment below his video is that when we think about dark matter, it's possible that dark matter is an actual entity which causes additional gravitational force inside galaxies, or it might be just a new law of gravity, and there is no actual entity causing it. It's just the same amount of matter cause different form of gravity. So in one way or another, there's still like a law governing this causation. Um, so it's a bit unclear how you can get rid of this whole notion of physical laws. I don't know. He claims it's some sort of form of superstition, but I don't know how to overcome it. Um, what what kind of outside the box thinking this requires.